we are again back to basics, because for some of the later chapters again we need some background, and I thought that it is better to cover it. We also had some doubt about Z transforms, so I thought that we should cover that. So today we will look at some properties of the Z transform, more on those properties which we usually do not see. We see the tables and other things, and take a brief look at what are eigenvectors and eigenvalues, because that is going to be used very soon in defining a quantity which is very common, which is called the innovations. So before we define start discussing the concept of innovations, it is important to know what are eigenvectors and eigenvalues of a matrix. So we start with the discrete Fourier transform. That is defined, as we know, by this infinite series, right? And the inverse discrete Fourier transform is given by this integral. It is an integral because the discrete Fourier transform is a continuous function of omega. This is discrete, but this is continuous function of omega, and this is very easy to prove. If you just substitute this expression here, take the summation out, that is somewhat simple to prove. You just have to substitute this expression here. So then it will look like an integral inside a summation. It will look like this if you substitute, and you can take the summation out, then it will look like a summation and inside an integral. Are you able to follow? So here you will get xn. So you have to only evaluate that for this integral is going to be, you can easily see that this integral will be equal to 0 if n is not equal to m, that is this side you have xm, here you have, this integral will look like sigma xm m is equal to minus infinity to plus infinity some integral. If you exchange the summations, I am not doing the full thing, then it will turn out, here you have n, and when you replace this you have to put m here, because otherwise they will get, it is not the same n. You are evaluating this for a particular n, so n is fixed while m is varying, so m you have to give a different index. That is why I have given m. It will turn out that this integral is equal to 0 for m not equal to n. So all that xm terms will go, only the xn term will remain, and that will, whose value will be equal to 1. Very simple to prove, just ordinary integral knowledge will be sufficient. So now there is always a question of when this is defined. Remember, whenever we are defining anything by an infinite series, this we must remember. We are generally not conscious, but we should be conscious about when this is defined, that is when this sum of the series converges. Okay, if it does not converge, then this has no meaning. So now so we have to find out, so we are trying to find, that is why we try to find conditions under which this value does not tend to infinity for any omega. Okay, so if you want to find such conditions, so one condition is that if you take this is naturally less than or equal to this. How? Why? Because magnitude of this is magnitude of this. Now magnitude of AB is always less than magnitude of A into magnitude of B, right? So therefore I can write this is less than or equal to this. What is the magnitude of this? It is 1, because it is e to the power j theta. So this is less than or equal to this. So if this sum is less than infinity, this sum will also be less than infinity. This says that, so this is called the known as the absolute summability condition. That is, if you have a sequence xn and if you find that the sum of the magnitudes of xn can go positive and negative of course, but if the sum of the magnitudes is less than infinity, infinite sum of the sequence, then this exists. Such sequences are sometimes called stable sequences. If this condition is satisfied, this is called the absolute summability condition. This shows that then this exists. So, and why is it called stable? It is called, why this term stable has been coined? Because of a particular result from stability. And that result says that suppose you have a filter, this is the convolution integral. Now suppose we are talking about bounded input, bounded output stability, that is, if the input is bounded, what is the condition? That the output will also be bounded. So let the input be bounded. So for all L, magnitude of UL must be less than m. M is some fixed number, however large. So we are considering a bounded input. If m is bounded, u is bounded, then what is the, how y is bounded? So you can put the maximum value of u here, m every time, and not only that, you can, just to make the sum, we are trying to see when the sum reaches the maximum under this condition. So it will be maximum when all magnitudes will be m, and not only that, when this will be minus, this will be minus, when this will be plus, this will be plus, then all the terms will be plus and it will add to the maximum. Otherwise plus minus may cancel. So I mean, just putting m will not do, just putting u is equal to m will not do. So we have to match the sign with the sign of hk such that every time all the terms in the summation will be positive and it will add up to the maximum. So if we do that, so that is why I have substituted m, sgn, hk. Sgn means the signum function, which is plus 1 if hk is positive and minus 1 if hk is negative. So then all these terms will, so that will be equal to this, because now plus 1 minus 1 multiplied by this will be magnitude of hk, this signum function when you take it here. So now m is bounded, so m is a constant, so it will come out of the summation actually. So if, since m is bounded, y will be bounded if this is bounded. Naturally. So the condition that under all, so if this is bounded, this system is bounded input, bounded output stable, right. So this is called the absolute summability condition, absolute summability, because you are taking absolute, you are taking magnitude and then you are summing, and that sum should converge to a bounded value, though it is an infinite sum. So if this happens, then that is why such sequences are called stable sequences. So stable sequence means if you, using that sequence as impulse response coefficients, if you implement a filter, then that filter is going to represent a bounded input, bounded output linear system, right. That is why it is called stable. So if this is less than infinity, then system is bounded input, bounded output stable, and then h to the power j omega exists. See, otherwise h to the power j omega does not exist. We are sometimes, we are, we deal with, we first learn in our courses, we first learn Laplace transform. Now Laplace transform existence condition and Fourier transform existence condition is not same. Laplace transform exists for many values of alpha. There is an e to the power minus alpha t there, which is not here, right. So the existence condition of e to the power j omega is more stringent, that is, in many cases e to the power j omega will not exist, but the Laplace transform will exist, Z transform will exist, as we shall see. Okay. So I mean, just putting, I mean, for all functions we cannot talk about a Fourier transform unless it converges. So now to to generalize that question, let us talk about the Z transform. So now we have taken this is a more generalized transform in the sense that Z is any complex number. See, what is a transform? Transform is that basically it is like a reflected domain, just like you are seeing something through a mirror. So rather than studying the function xt, which may be difficult to study, you are transforming xt to another domain called Z, and you are studying the behavior of xt through the behavior of xz, because it is mathematically more convenient, nothing else. I mean, typically because various kinds of time domain properties will become algebraic properties. So time shifting property will be z times something. I mean, all your differential equation kind of operations will all become algebraic operations under suitable conditions. So you can very easily deal with it. That's why we take the function xt to the transform domain and then study it there. Okay, this is the sole purpose. Xz as such does not have any much of physical significance. Sometimes it has with respect to energy and all, but as such the real quantity is the function xt, or in this case xn. Okay, so here we are trying to study it, defining it in terms of an arbitrary complex variable z. See, in the previous case we were studying it through a function omega and e to the power j omega n. Okay, so now we are not doing that. Now we have further generalized it. So obviously here also there will be a region of convergence. So for some value of z this will converge, and for some values of z it will not converge. So we must remember this region of convergence. Suppose, just to evaluate when it will converge, let us choose z is equal to r to the power j theta. That is, I am trying to represent a complex number in the polar notation. Okay. So then now if I put this here, I will get this. See, now that this looks like the Fourier transform, right, because this is e to the power j n theta, which was previously like j n omega. So it says it is the same thing. So now when will this converge? We already know the Fourier transform condition. So if this is less than infinity, then this will converge, correct? So this defines the region of convergence for xz. There are two interesting things to note. First of all, that the region of convergence depends only on r. So whether the radius is going to be smaller or bigger. So all regions of convergences are essentially characterized by circles in the z plane. So it is going to be either less than r or it is going to be greater than r, but it is always going to be on a circle, because it is characterized only by r, right? So that's an interesting thing to note. Now this we had seen previously also, just mentioning it again, that two different sequences may have the same xz. So why? So this is that old example, I think, which we did. So if this is the sequence xn, un is the unit step function, then I have this as a z transform. Simple, just by putting minus infinity to plus infinity becomes 0 to infinity, because un is 0 for all n less than 0. So then this will sum if the magnitude of this is less than 1. So and it will sum to this. So you have z by z minus a as a z transform, and the region of convergence becomes this. This is very important. So this function has this z transform over this region of convergence. That is a complete statement. This function has this z transform is not a complete statement to make. I mean, the function cannot be uniquely obtained unless you specify also the region of convergence, which we do not do usually. So on the other hand, this function, which is a totally different function, also has the same z transform. This is just by mechanically working. See, minus n minus 1 is a u. This will also exist for positive arguments of this. So this will exist. This function will be non-zero or 1 only for these arguments -1 to -infinity. So now if you just do elementary transformations, you will get that is also equal to z by z minus a, but now the region of convergence is mod z less than a. So these two are totally different functions, give the same z transform but with different regions of convergence. So this is a fact which we should remember. Yes.
So how do we assess what is the region of convergence for a particular z transform?
By you have to use different properties. For example, in this case we are trying to use the property that 1 plus x plus x, we are trying to take the sequence, trying to cast it in a particular form, and then using our result that 1 plus x square up to infinity sums to 1 by 1 minus x provided mod x less than 1. We are using that property.
So but in these two cases,
yeah,
the formula is same. So shouldn't it be yielding the same result?
No. Obviously the formula is same, so what? But formula will always be same. But these two are different sequences. See, this sequence with n, this is a to the power n and this is un. So for n greater than 0 it will be a1 a square like that. This is going to be minus a to the power n first of all. So it is a totally different function. But it so happens that they yield the same when over the regions where they sum, you get the same sum, but these z values have to be different for in both cases. That's all. Right. Now again we know that if the ROC or the region of convergence includes the unit, or rather if the system is Bibo stable, now we are putting the other result. Now when does the Fourier transform exist? Fourier transform exists means what is the Fourier transform? Fourier transform is nothing but the Z transform evaluated over the unit circle, because over the unit circle Z is equal to e to the power minus j omega, right. So in the Fourier transform you put Z is equal to e to the power minus j omega. So you are evaluating the Z transform on the unit circle. Now, and if the Fourier transform exists, then that sum converges, which means that the unit circle must be inside the region of convergence of the Z transform, otherwise it will not converge on the unit circle. So if the system is Bibo stable, then the Fourier transform exists and the region of convergence of the Z transform includes the unit circle. So it will be something like this, probably the region of convergence will be something like this. That is the outside of this some circle, it may be like this, it may be between two circles also, that depends on. So this is the first property which we can get, and the second thing is, now here in many cases we will get a function in terms of, that is we will get a sequence in terms of two sequences, right. In many cases we can express a sequence as a sum of two sequences, it can happen. Now it can also happen that x1n has a Z transform x1z over some region of convergence, and x2z x2n has another Z transform x2z over some other region of convergence. It is possible. Simply if you add these two up, if you define another function which is like this, which is this plus this, you can define, right, and then you can now remember that if then what is the Z transform of xn, that is the question. So the Z transform of xn will be simply the sum of this when only, what will be its region of convergence? It will be the intersection of the region of convergence of this and the region of convergence of this, because whenever this will be defined, whenever this has to exist and this has to exist, both have to exist. So it must exist on points where both exist. So therefore it must be on an intersection of the region of convergence. For example, in this case there is no intersection. So if you sum these two sequences, its Z transform does not exist. Okay. So we have to remember this. Now we have known that such sequences, for example, suppose x1n is xn for all n greater than or equal to 0 and 0 for n less than 0. And similarly, suppose x2n is just opposite, that is it is xn if that is xn means has some non-zero value for n less than 0 and it is always 0 for n greater than or equal to 0. These sequences we call causal and anti-causal. Why? Because of the convolution property. That is, if we convolve with this, we will always find that the output is affected only by past values. If we convolve with this, we will always find that the output is only affected by future values. True? This we have discussed many times, that hn minus k gets affected by u, k and all. So these that is why, so if you they are called causal and anti-causal, because if you use these sequences as impulse responses, then the corresponding filters will be causal or anti-causal. That is why, I mean, otherwise there is as such no meaning of a sequence being causal. Causality always comes when there is a cause and there is a effect. So there has to be two sequences. So when we say sequence is causal, we mean that if we use that sequence as an impulse response of some filter, then that filter will be causal or anti-causal. That is what we mean. So interestingly, now if you take any sequence xn, it can always be divided into this whole sum, which is from minus infinity to plus infinity, can be broken up like this. One is from minus infinity to minus 1, another is from 0 to infinity. I have just separated the terms, right. So now if I make a definition of x1n and x2n like this, that is take all the values of xn for n less than 0 and make into x2n, take all the values of n for n greater than 0 and make it into x1n. I can always define, and then if I add them, I will get the overall function from minus infinity to overall total sequence I will get. So what will be the x2z corresponding to x2n and x1z corresponding to x1n? They will be these two, and this will be those terms. So now when does x2z exist? If this sum is infinity, this is x2z. So if this is infinity, this will exist, and if this is less than infinity and if this is less than infinity, this will exist. Same formula we are using, previous argument we are using. Only thing is that these two may not exist for the same value of r. That's what we have to see. Now if you see this condition, typically what will you know? See, n is negative here, which means that the power of r are actually positive. So which means that if this has to be less than infinity, r has to be less than a quantity. If r becomes greater than something, then this sum will diverge. This sum generally increases with increasing values of r because it is positive powers of r. So obviously the region of convergence is going to be inside some circle for this set of terms. R has to be less than something, then it will converge. That sort of condition we will get. So the condition for this will obviously be some radius, and the inside of a radius will be the region of convergence for this to be true. On the other hand, for this to be true, this is not infinity, this is 0 to infinity. For this to be true, obviously r has to be less than some quantity. This here, no, one second, x2z, okay, this is okay, so this is minus n, okay. For x1z, now so this is the condition, there is some r2 star and r has to be less than this. Now x1z will exist. What is the term x1z? x1z is this. So here n is positive and r to the power minus n, that means r has to be greater than a quantity. So the convergence region for x1z will typically be the outside of a circle. So this gives us an idea that if we have an anti-causal sequence, which is this, then the region of convergence is generally the inside of a circle. If we have a causal sequence, which we usually deal with, the region of convergence is always outside some circle, right? This needs to be remembered, because that's why we always say that for a stable sequence poles should be inside unit circle, as we will see this result, because then the poles are not covered by the region of convergence. Poles are where the function goes to infinity, that those values of z are called poles. So obviously poles are not included in the region of convergence. So poles and for a stable thing, the region of convergence is the whole infinite plane excepting the inside of the circle. So that is why we say that all poles must be inside, because the function must converge at all other points, right? So properties of, so in general what will happen now? So you see, if I take a general sequence, some part of it which is anti-causal, some part of it which is causal, then if you merge these two, then what will be the condition for xz to exist? That it should exist on the, it will be r less than some r2 star and r greater than some r1 star. So it will be a ring in general. This is r2 star and this is r1 star. If that happens, then the Z transform will exist in this ring by these two conditions. This is r2 star and inside is r1 star by these two conditions. Then the overall Z transform, which is the sum of these two, will exist in this annular region. And if this annular region now contains the unit circle, then it will be stable and the Fourier transform will exist. If the annular region does not contain the unit circle, then the system will be unstable. Then the Z transform does not exist. If R1 is greater than R2, then the Z transform does not exist, because there is no intersection between the regions of convergence. There is no point in Z where both x1z and x2z will converge. So therefore the sum of xz cannot exist. So the basic properties are that generally region of convergence is a ring, is an annular region, as we have seen, and it cannot contain poles, of course, because at the region of convergence the value of xz is finite, and at poles the value of xz is infinite. So it cannot contain poles. Region of convergence can never contain poles. Now interestingly, we in many cases we deal with finite duration sequences, that is sequences which are 0, then for some between some two values of n it becomes non-zero and again becomes 0. For such sequences Z transform will always exist, because it is a finite sum. Infinite sum will become finite sum. It will always exist excepting at maybe at 0 and infinity. Why? Because it contains Z inverse and Z kind of terms. See, for positive powers of n it contains Z inverse terms, and for negative powers of n it contains Z square kind of terms. So if these sums, if such terms, that is Z to the power I and Z to the power minus I, have to be finite, then Z cannot be 0 here and Z cannot be infinity here. So excepting for those 2 points, that is Z is equal to 0 and Z is equal to infinity, which you can think of as a infinite radius circle, excepting those 2 points, at all other points this sum will be finite, simply because it contains a finite number of terms. So there is no problem, whole plane will be region of convergence if you have finite duration sequences. Now we must remember that there is no as such no connection between this causal, non-causal, stable and unstable. That is, you can have a causal unstable, you can have a causal stable, non-causal stable, non-causal unstable, all combinations are possible. So why we are talking about non-causality is because, as I said, that in many signal processing applications you actually use non-causal filters. So we need to know their properties as well. For example, this filter, if the region of convergence is like this is the hatched part, and if this is the unit circle, then it is a causal unstable filter. Why it is causal? Because it is the region of convergence is outside of some radius, so it is causal sequence, and it does not contain the unit circle, so it is unstable. So the region of convergence, so this region of convergence will hold for a causal unstable filter. Similarly, here you can get a non-causal but stable filter. Non-causal because it is the interior of a circle, and stable because it contains the unit circle. So you can have all sorts of combinations. Okay. And obviously for causal systems, poles must be within the unit disk. That is, if the system has to be stable, then the region of convergence must include the unit circle. So this should be extended, then it will be causal and stable, and this whole region cannot contain the poles. So therefore, where are the poles then? Poles are here inside. So that means they must be inside the unit circle if the system is causal and stable. That is, that kind of systems we are mainly interested in. And remember that what did we define as a minimum phase system? It is something which is stable and inverse stable. That is, Hz is stable and Hz inverse and H inverse Z is also stable. So if you want to have that, now what are the poles of H inverse Z? They are the zeros of Hz. Just imagine Az by Bz. So simply speaking, so H inverse Z will be Bz by Az. So the zeros of Hz are the poles of H inverse Z and vice versa. So if both have to be stable, then both poles and zeros of Hz must be within the unit circle, because zeros will become poles. So if Hz has a zero outside the unit circle, it will become a pole of H inverse Z. So then H inverse Z will be unstable. So that cannot happen. So for minimum phase systems, all pole zeros are inside the unit circle, poles and zeros both. Okay. This is just, I am just trying to emphasize the fact, because at this level, normally at a lower level when we study, let's say for undergraduates, we do not bother about these things too much. We use tables and things like that. But here I wanted to stress that point, that region of convergence things, and also see one thing we also assume is that all Z transforms will be expressible as some Bz by Az. That is not correct. There are some Z transform which can appear as a ratio of two polynomials. All Z transform may not be that. There may be any arbitrary form of Z. Right. So not necessary that Z transforms are always expressible as Z minus A by Z plus A kind of forms. So if but in our earlier classes we generally assume that form and then talk about other things. So here we have not assumed anything like that, right? And we sometimes talk about, so far we have always talked about what are known as two-sided Z transform. That is, the summation is from minus infinity to plus infinity. That is very necessary when this xn can contain anti-causal terms. Otherwise, it will not be properly defined. See, if you take a one-sided transform, then you are not at all talking about what happened to xn when n was negative. So for all sequences, so suppose you have a sequence, say -1, -2, 0, 3, 4, 5, and this is your 0 point. This is the n is equal to 0 value. Now you can have anything here, and just if you match these, they will have the same one-sided Z transform. So then the inverse will not be unique, right. So, whenever if we only if we know that this xn is a causal sequence, then the one-sided and two-sided Z transforms will be same. Then also there is problem, because if you are just given a differential equation and if it has non-zero initial conditions, and if you are just given the input from 0, how do you get the output? Because the output was non-zero before n is equal to 0. So you must be given something about it. So then if you are given initial conditions, then only you can use the one-sided Z transform. If you are not given the initial transition, if you are not given the initial condition, you cannot use the one-sided Z transform, right. So there are some such cases. So okay, so this is I wanted to discuss these points because sometimes these will arise. Now we will talk about another concept. This is a totally different concept which talks about matrices. We will consider real matrices for the time being, that is whose elements are real numbers, and here we are talking of square matrices. Okay. So maybe is this familiar to you, eigenvalues and eigenvectors? Do you know what are eigenvalues? I think it is covered in all undergraduate programs, but maybe so we will just go through it. Okay. So because we will, in many cases, actually what happens is that matrix is a complex quantity. I mean, it is a collection of m square numbers in general. So it is very difficult to understand what is happening. So sometimes if you transform the matrix in certain ways, then you can understand nice properties of the matrix. Okay, this is happening. That is very interesting, important to understand. So therefore we will be transforming the matrices in various ways, and we will also try to know, in some cases we will try to know things like what is the strength of a matrix. What do you mean by strength of a matrix? After all, what is a matrix? A matrix can be seen as a transformation of vectors. So if you multiply a matrix by a vector, you get another vector. So then many times we would like to know that what is the relationship between these two vectors. So if I take a vector along this direction and then multiply this vector by the matrix, two things will happen. Firstly, the length of the vector will become larger, may become larger or smaller, and its direction may change. These two things will happen if you generally multiply it by a matrix. Now we will be interested to know whether it grows larger or whether it grows smaller. For example, what is stability? When we have xk plus 1 equal to axk, our famous linear system equation. So what are we doing? We are taking a state vector and then multiplying it by the matrix A to get the next state vector. So if it converges, we say that the length of these state vectors must continuously decrease. Otherwise, why should it come to 0? So it must be related to this property of the matrix, that whether it stretches the vector or it contracts the vector, whether it through which angle does it turn, and things like that. So to characterize that, eigenvalues are important. That's why we say that the eigenvalue should be less than unity for discrete systems. Okay, poles should be within the unit circle. So eigenvalues of the matrix should be less than unity, so that every time it will get multiplied by, its length will be less than the length of the previous vector, right. So to understand these concepts, we need to understand these concepts are typically analyzed through eigenvalues and eigenvectors. Okay. So what is this is the definition of an eigenvalue, that if you take R is let us say an m into m matrix, Q is an m into 1 vector. So if you can find out a vector q and a number lambda such that this equation is satisfied, then the number lambda is called the eigenvalue and the vector q is called the eigenvector corresponding to lambda. So you have, for a matrix, you have a number of eigenvalues, and for each eigenvalue you will have eigenvectors. This is the case. All right. Now the point is, how do you know the eigenvalues? If you just take it this side, you can get r minus lambda I equal to 0, rather r minus lambda I into q is equal to 0. You take it this side. So it turns out that to get lambda you have to solve this equation. Determinant of r minus lambda I should be equal to 0. So this will be a, in general this will be a, this equation will be an mth order polynomial equation in lambda. See, lambda is an unknown, all others are numbers, right. So if you have 1 2 as r minus lambda I, so you have 1 minus lambda 2 minus lambda as this matrix. So what will be its determinant? It will be 1 minus lambda into 2 minus lambda equal to 0. This is the equation. So it becomes a second order polynomial in lambda. Now if you solve this polynomial equation, you can always solve it. So it will give you n numbers, because an nth order polynomial will have n roots. So those numbers are the eigenvalues. Once you, so now after solving this you have got the eigenvalues. Now you put the eigenvalue in this equation, that is substitute the value, that value of lambda, then you get an equation like this. It becomes like an equation ax equal to 0. So you solve, it is nothing but a set of linear simultaneous equations whose unknowns are the coefficients of q1, q2, q3, that is the elements of this vector. Just simply solve the equation r minus lambda into q equal to 0, you will get the eigenvector. It turns out that eigenvectors are length independent, that is, if q is an eigenvector, then if you multiply q by any number 2, 3, 4, 5, any real number, and that is if you stretch all the numbers by the same amount, it still remains an eigenvector. So we generally talk about eigenvectors of unit length. Actually eigenvector only indicates a direction, there is no concept of length. So, I mean, along that direction any vector of any length will be an eigenvector. That is obvious for here, from here. If you take a q dash equal to some aq, still this equation is satisfied. If q satisfies this equation and a is a number, then q dash also satisfies this equation. So it is also an eigenvector. So we generally talk about eigenvectors whose length is equal to 1. We fix the length generally. But lambda can be a real or complex conjugate pair, remember, because this equation is this equation is a nth order equation, so it will have real or complex roots. But since all the coefficients of this equation are real, therefore if you have complex roots, they will occur in conjugate pairs always, otherwise you cannot get real coefficients, correct. So therefore lambda will occur in real or complex conjugate pair. Now we will look at properties for lambda being distinct. Actually what happens is that if lambda is not distinct, then the direction of the eigenvector also is not always guaranteed. For example, I mean, a best example is take the identity matrix, that is an nth order matrix which is 1 1 1 1 1, all ones, okay. Incidentally it is a diagonal matrix, but all its eigenvectors are, I mean, what are its eigenvalues? All ones. So there are, all eigenvalues are repeated, because r into q is equal to lambda into q for any q, and for lambda equal to 1, because it is an identity matrix. So therefore r into q is equal to q for any q, remember that, for any q. So basically, so if all the eigenvalues are repeated, then the space of then any vector is an eigenvector. So you cannot say that even the direction is fixed, you cannot say that. So in that case, if you, I mean, you have to choose your direction. But so let us talk about the case, because if you want to know properties, then you should understand these properties, that is, if the lambda are distinct, then what happens, because then we get very interesting properties of the eigenvalues and the eigenvectors, which we are going to extensively use in this course. So first of all, let us see first this property. This property is of course true for any I mean repeated or distinct eigenvalues. That is, if lambda is an eigenvalue for R, then lambda to the power k is an eigenvalue of R to the power k. That is very simple to prove, because R to the power q, say R to the power k q is equal to what? Is equal to R to the power k minus 1 into R q. R is a matrix. So it is equal to R to the power k minus 1 into lambda q. So you go on replacing, then now lambda is a scalar, so it will come here. So again take another R out. In this case every R will generate a lambda. So you will get that R to the power q kq is equal to lambda to the power kq, which means that if lambda is an eigenvalue for R, then lambda to the power k is an eigenvalue of R to the power k. Very simple property to prove, and this happens for whether it is repeated or distinct. Now interesting thing is that these eigenvectors have very nice properties, which is what is going to be exploited in this course. They have very nice properties, and one of the most important properties is this, that is, for distinct eigenvalues the eigenvectors are orthogonal. You know, we always prefer, whenever we choose a coordinate system, we always prefer that our coordinate systems are perpendicular, because then we can go along one without changing the others, without affecting the others. So we always look for perpendicular coordinate systems, and it so happens that for any matrix these eigenvectors are perpendicular to each other, right? When a vector is perpendicular to another, its inner product is 0. True? So this is the first property. This can be again very easily proved. How you will prove this? Think about proving these properties. Why? I am telling you, if you we can discuss this in a future class. They are generally easy properties to prove. All you have to use is RQ equal to lambda q. No high great knowledge is required. But if you do this, then then the properties of the eigenvector and eigenvalues will get embedded more deeply in your mind. So try to prove these. We can discuss these in a tutorial class. They are very, quite simple to prove actually. So obviously if qi transpose qj equal to 0, this is the next property which is important. This is actually this is a more general property than this. This says that for distinct lambda I, all the qi, they form a linearly independent set. Means what? What is a set of, these are vectors, right? These are vectors. So what do we mean by a set of vectors are linearly independent? When any one of them cannot be generated by a linear combination of the others, which means that all of them are needed. You cannot really remove one and then say that okay, using the others I can generate this one. That is not possible. So all these sets are needed. So whenever you require, so they are the minimum range of vectors needed to actually characterize a full n dimensional space. You see, if you only have vectors in this plane, and if you try to characterize them in terms of 3 vectors, say you say that all vectors I will express in terms of x1, x2, x3, then somebody is going to say that it is not needed. You don't need x3. You just try to work with x1 and x2. Any description that you can get with x1, x2, x3, you can also get with x1, x2, because this is a 2-dimensional space. So in general, when we have our vectors are all m dimensional q's, because the dimension of this space is m. So and these qi's are linearly independent vectors, m linearly independent vectors, because there are m eigenvalues, capital M. So which means that using these, so that these vectors can actually, there are 2 things which are being said, that these vectors can serve as a coordinate system because they are linearly independent. So they will characterize the whole space. So any vector can be expressed as a sum of this. That is the first thing which is being said. And second thing which is being said is that these coordinates, they are not only coordinates, they are perpendicular set of coordinates. So these vectors really serve as very useful coordinate bases for representing general n dimensional vectors. So in many cases we will represent our vector processes on a coordinate system which will be based on the eigenvectors of their autocorrelation sequences, and then we will get very good understanding as to what is happening to the process. So basically these are used for coordinate transformation, and that is used. So if you have R as a matrix, this is the last result and we will stop after this, that if you have a matrix R, then it can always be expressed like this. That is, you can always, and vice versa, these two results are there, where this becomes a diagonal matrix. So you can diagonalize any symmetric matrix R by using the eigenvectors. These Q's are the eigenvectors. Yeah. And similarly, if you have so similarly R can be expressed as a sum like this with these with a set of diagonal matrices. All right. So just remember this, and we will start using it in the next class. Thank you very much.